endeavor, our attention is focused to multiple integrals. Multiple integrals play a role of a prelude to vector fields. Therefore, to deal with the problems associated with vector fields, we need to have a little hang of multiple integrals. So that's why we learn multiple integrals. Of course, there are some other applications as well. However, in this endeavor, we focus our attention to double and triple integrals and how we evaluate them, and also the transformations which can be used in this endeavor to solve or to evaluate double and triple integrals. So that's what we cover in this section. 3.1, Introduction to Multiple Integrals. So there are two types in this case. The first is double integrals. The second is triple integrals. So first we will focus to double integrals. Let's consider this area, the area bounded by these four lines. So if you sketch them, you know this is the x-axis represents y is equal to 0. This x is equal to 1, which is a line parallel to y-axis. This x is equal to 3, and the line y is equal to x plus 1 has the gradient 1 and intercept 1. Therefore, intercept y-axis intercept is 1 and its gradient is 1. Therefore, it has some uphill slope like this. So we try to find this area. Now, in fact, there are three ways to find this area. First is that you can consider this as a trapezium, and using that you can find the area. So by doing so, we exactly know what the area of this shape is, right? So this is a trapezium. Therefore, you know how to find the area. So average of two parallel sides. So this length is 2, this length is 4. Therefore, the average is 2 plus 4 divided by 2 times the distance between these two lines. So you multiply it by 2. So you will end up with 6. So it's 6 square units. Now we'll use simple integral to evaluate this. We have gone through that in our A levels, so but we'll go through that. Then the third method, we consider double integral. So in all these three methods, you get the same answer. So that will justify the correctness and the physical interpretation of this double integral. So that's the basic idea. So the area is 6. Now we will move to the next portion. Now we consider a strip whose width is delta x. So now we are going to find the area of this. So we will first consider the infinitesimal area, this area. Its height is y. When y is given by x plus 1, the height is y, the width is delta x. You can consider this rectangle. When when delta x goes to 0, this error will go to 0. Therefore, you don't have to worry about it. So the infinitesimal area is y is equal to delta x. Now, the total area can be taken like this, y delta x. Here we replace delta x by dx because delta x goes to 0, just to minimize that error. The limits of delta x are from 1 to 3, right? Lower limit is 1, upper limit is 3. Therefore, you will end up with this. So in this case, you know, y goes from here the value of y is given by x plus 1, right? X plus 1. Now you plug in that. Now it's a simple integral. So this will give you x squared over 2. This will give you x. These are the limits. So first you plug in the upper limit, then you plug in the lower limit. When you simplify this, you get 6. So the same answer. So that will justify the correctness of this, and also already we are familiar with this one. Now we will move to our last way of computing this area. That is the use of double integral. Now, again we will consider the shape, this shape, right, the area, and we all know these lines, how we sketch them. Now, again we will take this as delta x, an infinitesimal portion of the x-axis, and this delta y. I will write it here, delta y. Now, in this case, in the case of a double integral, the infinitesimal area can be considered like this, right. The small box give or the small rectangle gives you the infinitesimal area. Now, here there is a little problem with the limit. So, we need to be very careful when you assign the limits. That is why you have this diagram here. I will come back to this later, right. First, we will consider the infinitesimal area. So, the infinitesimal area, as we know, it is delta x, delta y. It is the area of this rectangle. Now, the total area can be obtained by the double integral. So, when delta x and delta y go to 0, you will end up with dx dy, but for the sake of simplicity, I will explain it why I do it later, right. I will swap these two. I will first write dy and then I write dx. Now, with this setup, when you use a double integral, this dy, now there are two variables here. You have to note that there are two variables, namely in this case x and y. So, y associates with this integral, right. Y associates with this integral and x associates with this one. So, that is how it works. This is like a bracket, like if you want you can assign a pair of brackets like this. So, this is a separate entity where y is governed by this integral sign and x is governed by this integral sign, right. Now, first you need to focus on the center. You have to put your focus to the center, this one. Once you evaluate this, you go to the next integral. That is how you do it. We will see whether you get the same answer when you deal with this double integral. Again, I did not explain you the limits. The limits go like this. Now, this is the infinitesimal area dy dx. Now, first you have to assign the limits of y. Now, this is how you do it. Now, this is our area. This line is x is equal to 1, right. Let me write it here. X is equal to 1. This line is x is equal to 3. Here, this line. At the same time, this is y is equal to 0. This line is y is equal to x plus 1. Now, here we need to consider the limit of y. Now, in this diagram, you know, we need to consider the area bounded by these 4 lines. Therefore, y varies, or y goes from this value to this value. There is no specific value, this value to this value, right. Here the value of y is 0, but along this line the value of y is x plus 1, it is not a constant, right. Value of y is x plus 1. Therefore, this is the lower limit, this is the upper limit. So, here lower limit should be 0, upper limit is x plus 1. Usually, when you deal with the simple integrals, you do not get variables as limits. But in this case, right, when you deal with double integrals, for example, when you assign the limits of y, you might get the other variables in limits sometimes. It is not a must, but you may get the other variables in the limits. So, other variables means the remaining variables. Now, x is the variable to be considered in the next level. So, that variable should be there, can be there or may be there, right. Sometimes you might end up with constants as well, but in this particular problem, like for example, if we had a line like a horizontal line, then y is a constant, but in this case it is slanted, it has a slope, therefore, it has some variable x in the equation, therefore, you have x plus 1 as the limit. And then look, these arrows says how y varies, the vertical arrows. At the same time, x goes from like we consider the area bounded by these 4 lines. Therefore, variable x varies from here to here. So, 1 to 3, this 1, these 3, but everywhere, not even here, everywhere like 1 to 3, this is how it varies. So, limits of x can be considered like this. Now, look what happens. If you look at the diagram carefully, these horizontal arrows and the vertical arrows, these are the vertical arrows, intersect only in this area, right? You can see the checks like some mesh like thing, but in the other area, like in the other portions, like here, even though you have the horizontal arrows here, you don't have the vertical arrows. Here you have, like if I extend this diagram, here I can have a vertical arrow, but I don't have the horizontal arrows. Here I can have vertical arrows here, but I don't have the horizontal arrows. But both arrows are only in this, I mean you can see both arrows, or arrows in both arrows directed to both sides can be visible only in this area. So, that is the area we consider. So, x goes from 0 to x plus 1, y goes from 1 to 3. Now, it is a regular evaluation after that. Now, when you integrate 1, you get y. This is the lower limit, this is the upper limit. So, you have them. These are the limits of x, but you do not have to worry about that. You pay your attention to this one at the first place, right? In the first step, that is what you do. Now, when you integrate 1, you get y. These are the limits. So, you substitute those limits. X plus 1 comes first minus the lower limit. But we keep the other part intact. We do not touch it. Now, when you simplify this, you get x plus 1. Now, it is a simple integral. And if you want to go back here, you have the same integral. So, both are the same. After that, we can evaluate it. You know, this x squared over 2 plus x, the integral of this one. So, this is the upper limit and the lower limit. So, first you plug in the upper limit minus the lower limit. When you simplify this, you will get 6. So, that is how you use a double integral to evaluate the area, and at the same time, this is how you evaluate it. Like you first consider the center of the integral, you first sort it out and come up with the value, and then you deal with the outside variable, or the variable sitting outside. So, that is how you do it. Even in the triple integrals, you have the same pattern, same shape. Now, the last one. Now, I told you that for some reason I swapped these two, like here x comes first, but here y comes first. I changed the order. I changed the order because if I keep it like dx dy, the first problem that I wanted to explain would have been difficult, but here it is not that difficult. That is why I solved this one. Now, if I kept dx first, then it will be difficult to evaluate this one. Let us see what happens if you reverse the order. By reversing the order, again if you consider this as this the width of this one as delta x, this delta y, again the infinitesimal area is delta x delta y. But here we have a little problem. When you have delta x first, so dx comes first. So, you have to first assign the limits of dx or limits of x. But here we have a little problem. In this area, in this portion, in this rectangle, x goes from 1 to 3. So, that is fine, x goes from 1 to 3. But after that, x goes from this line to this line. But earlier we did not have that problem, because earlier when we dealt with y as the first variable, always you can see y goes from here to here. So, you know that the change is always consistent, 0 to here. But in this case it is different, right? Look, in this area, now x comes the first, now x plays the role of the first variable. So, x goes from 1 to 3, that is okay. But after that, It is not 1 to 3. It is from this line to this line. Right? Therefore, you have to consider this as two areas. I will take this as A1. I will take the rectangle, sorry, the triangle as A2. So I take A1 and A2. Now, in this area, what is sitting like the rectangle, the infinitesimal area is dx dy. But you know what happens here. The infinitesimal area is indicated like this because dx, delta x and delta y both go to 0. That is why we write it like that. Now, in this area, x goes from 1 to 3. Look, 1 to 3. Y goes from, here y is 0, 0 to 2. So, x goes from 1 to 3, y goes from 0 to 2. In the rectangle, x goes from this line to this line to this vertical line. X goes like this. But in this line, you have to make x the subject because we have to write the value or the expression for x. Here, you know, x is, let me write it here, x is equal to y minus 1. So, in the second integral, the limits of x sit like this, y minus 1 to 3, but in this portion, y goes from 2 to 4. Because the second variable, you do not have to worry about including the first variable. Second variable, you write the lower limit and the upper limit, right, 2 to 4. There again, you do not write it in terms of x. It is simply 2 to 4. Because in the second variable, according to this one, you know, let me again draw it there, how it works. In the triangle, x goes from here to here. Y goes from 2 to 4, so here to here. So these 4, sorry. You can see that both arrows intersect only in the triangle. Therefore, that's why we are happy to have the limits of y like that. Because because this would be sufficient for us. X goes from here to here, y goes from simply 2 to 4. So you can see that if you assign the limits like that in the second integral, both horizontal and vertical lines intersect here. So we do it like that. Here again, integrand is 1, variable is x. If you want, you can, for the sake of clarity, you can do it like this. It is x. If you integrate it, it is x. Limits are from 1 to 3. You keep the other part intact. You do not touch it. Here, again, the integrand is the integral is x. The limits are from y minus 1 to 3. Then you go from here to there. Here it is 3 minus 1. In this case, 3 minus what you have as your lower limit. So you have that. Now these two, so these are the limits. This 4 minus 5. Now it's a simple exercise after that. You get 2y here. These are the limits. Here you have 4y minus y squared over 2. These are the limits. You plug in those, you will end up with 6. Again, you get the same answer. However, this will be little tedious. That's why I solve these two first. Because once you change the order, sometimes one method is easier, the other method is not that easy. Therefore, with the application, you better choose the best way to evaluate it. So with this, we basically we have gone through the introductory part for the double integrals. However, we need to do some examples from this. So we'll do it in the next video. Okay, thank you.